We will wait for a few more minutes for more people to join, and then we'll start our today's session. Welcome all of you for today's session on the a study guide in the organic retrosynthesis problem solving approach. And this is our fifth session. So today we'll discuss some problem based on the it's not directly related to the week fifth topic covered by the professor. However, mostly all these problems are generally in aligned with these our topics about retrosynthetic analysis. So before moving to actual discussion, I would like to inform you that there will be a interactive session with the professor tomorrow at this time 15:30. So make sure you guys have attend this session tomorrow on the 25th of the Feb 2026. And you can ask the professor a question, so you can fill the Google form so for this as well. If you have any doubt, you can also ask directly to the professor while this live session. Okay, so moving to the taking some before moving to further part uh, in the actual problem for the today's session. So I would like to take the questions from the audience. So does you guys have any doubt regarding this topic or which is covered till this week six? So if you guys have any doubt, please let me know, and I will take some question after that if you don't have any doubt. Okay.
Till now it's okay.
Yeah. Sorry.
Uh,
Sorry.
till now it's okay, but I don't know when a lot of paper name reaction and the retrosynthesis will come. What will happen? Till now it's okay.
Okay, so mainly, yes. So basically, in this retrosynthesis, we also need parallelly some different name reactions, also need to some reagent, how this reagent works. So that background also parallelly we need. And that's why I generally, while solving some problem, I generally took on every class one or two name reaction just to uh, give you some understanding how these reactions work. So the time to time, I will try to put some name reactions in between the our regular solving problems, and also maybe in upcoming video, I will cover the actually the some reagents as well. So common reagent which are generally used, mainly oxidizing reagent, reducing reagent, along with the some common name reactions. So that sort of, and we have, I think, already covered some reducing reagent. So we haven't really covered a lot of oxidizing reagent that we will cover in the maybe in the next video. And as you mentioned, name reactions are very important. As you have seen, there are several name reactions like Wittig reaction, Claisen condensation reaction, which already we have seen some sub problem based on that, and also the Diel-Saldar reaction. That also we have discussed in the last video maybe. And if you look at the problems for these week 6, sorry, week 5, there are several name reactions also you may see in the assignment question. And that mainly the Wittig reaction that we have already seen. Additionally, there are Claisen rearrangement, Michael reaction, Corey-Tchaikovsky reaction, and the Nape reaction, the Luce reaction that we have already seen. Some name reactions, particularly the Clemenson reducing reactions, mainly Clemenson reduction, Burst reduction reaction, Luce reduction, Noiro reduction. We will see while studying this similar problem based on this. So I will take this name reaction topic in noted, and maybe in the next video I will try to cover more and more name reaction and some reagents. So okay, so we'll move to the some problems like I have shortlisted for today's session. Okay, so this is our first problem. So this is our target molecule, and we have to do the retrosynthetic analysis for this target molecule. So I will just draw it as a TM in the short form. So if you look at this target molecule, and here already the retrosynthesis is given because mainly we will see okay in this the first question. So you can see. So first we'll try to observe how the retrosynthesis has been done. So it will help us to solve these the problems in the future. So if you look at this retrosynthetic analysis of this molecule, which is uh, arildone molecule. So this is the name for this molecule, and so in this molecule, the first disconnection have been done at this point, and mainly, if you look at this disconnection, so this disconnection gives us this molecule, so which is uh, this negatively charged anion. So if you look at here, so this will be delta positive, and this is delta negative because this position is the alpha position to this carbonyl, and we get the negative charge here. And directly the synthetic equivalent for this has been given with the bromine, right? So here we have the bromine, or maybe bromine or any iodine or the any halogen group or good living group, we can say here. Also, the second disconnection has been done from this position, so we can have this alcohol, and remaining part is the bromo version. So if you do the linear synthesis of this molecule, how it will be? So we have the starting material with which having this methoxy group and the chloro substituent with this hydroxy. And if you perform the reaction of this with this bromo compound, so what happen in presence of the base? So base helps to form the anion at this O oxygen atom, and which followed by the SN2 uh, substitution reaction, we get the intermediate, which is this is the remaining part will be as it is. This oxygen is now substituted with this uh, chain, which has the this bromine. Right now, the another step is the reaction addition of this bromine part to the melon. So this is the malonate sort of group. If it was the ester, then it will be the malonate. But now in this case, is the keto version of this compound. So after creating this compound with this, after treating this compound with the this diketo, we can get, so that is diketo in presence of base. This reaction also proceed with the in presence of the base, because in presence of the base, this proton is get abstracted, we get the negatively charge. And once we get the negative charge at this position, so what happen? So this negative charge attacks uh, this. I will just draw the linearly now. Just a second. Okay. So this negative charge attacks on this carbon, and this bromo or the iodo get eliminated, right? And we get the compound in which this aromatic ring part is there along with this side chain, and this side chain now get substituted with this new part that I will write down with this different color, so it will be easy for understanding. So like this, right? So basically, we can substitute the ortho alpha position of this ketone with this alkyl part. And now this was our actual target molecule. If you look here on the previous slide, so this was our target molecule. This is very simple example, and just to explain the reactivity of this malonate, I have purposefully taken this compound. So if you have such compound, such group also. So this is the diethyl malonate, and this has various application in the synthetic chemistry, because if you look at here, so these two positions we can substitute. So let's do some linear synthesis with this molecule. So if you have some, let's say like this R, uh, their group, and in presence of the base, and if you add this group here, so these hydrogens can abstracted in place of base. And if you add this group alkyl bromide in excess more than 2 equivalent, so what we can get from this? So we can get double of 480, and this also same. So we can do the disubstitution of these R groups, not directly R. Anyway, so these R groups, right? And further utility of this reaction is in this one, if we can do the hydrolysis, so this group can directly convert into the acid group, and one of the acid group we can can also remove. So by By this manner, we can get actually the uh, extended. So first, initially, the one compound, one hydroxy group can so both this ester group convert into the acid, and this acid under heating uh, can potentially uh, we can remove this because both acyl group when they are on the same carbon atom, we can do the decarbonylation from this center. So that's what and if you look closely on the product form after this reaction, so which is this product. So basically we can increase the chain length with this type of approach, and we will see some example using such method in which uh, use of this dimalonate, and we did the dye substitution followed by elimination of this one of the ester group. And how this elimination occurs: first hydrolysis followed by decarbonylation reaction. So we'll see some examples in the latter part of this video only. I have some example listed further, so we'll see that one as well. Okay, so this is the same synthesis of this earlier example shown here, the linear synthesis. You can note down from here. It can just mention clear. That's the first step was the uh, O. This hydroxy group in place of base from the O negative, and then for the attack on this center further in the second step. So these hydrogens attached on these magnet, they uh, can be substituted with this addition of the base and the what we called this diketone 1,3 diketone, and we get our target molecule. The next example, so this is the second example. So if you look closely at the target molecule here, how the retrosynthesis of this target molecule has been done. So if you look closely here, so this is P double bond O Bu twice. So that's the phosphate group. So this phosphate group can be comes from the hydroxy group, and we'll see when we are going to see in the linear synthesis how this reaction works. Further, functional group inversion of this hydroxy group to the not hydroxy CH2OH group entirely, not only this hydroxy part, but this entire part along with this CH2 can be come from the uh, ester group. And further, the 1,2 carbon carbon bond cleavage. Yeah, this was the reaction that I have shown earlier. So this reaction either here disconnection gives these two starting materials. That is the dimethyl malonate along with. So this is the diethyl malonate and along with this alkyl bromide. So if you look at the linear synthesis also the similar. So this is the diethyl malonate in presence of base and this alkyl bromide. So it gives this. The first step was just alkylation. So as I mentioned earlier as well. So this hydrogen, they are acidic in nature, and in presence of the base, what happened in presence of the base? This proton get abstracted, so it forms the negative charge here. Once this negative charge form, this negative charge attack on this bromo carbon, and this bromide get eliminated, bromine get eliminated, Br negative. So we get this alkylated product, right? And once we get this alkylated product, so the second step was the reduction of this ester. So I have also mentioned in the last video the reducing agent, how the different reducing agent occurs. In this case, if you do the reduction, these sister groups can reduce to the hydroxy group. So what we get upon LiLH for addition, that is the reduction reaction. So we get, so this OPH part remain as it is. Now the ester groups get converted into the hydroxy group. And when we treat with this hydroxy group with the tosyl chloride, TSCl, so this both hydroxy group get protected with this tosylate. So this hydroxy group basically get protected with the tosylate as mentioned here. So you can see here. So once this tosyl product is formed, so what happen after this tosylation? So if we treat with this Na sodium phosphate, we- this group, so this is basically Na. This P negative, Na positive, right? So what we have did here, this hydroxy group was bad living group. We have converted this into the tosylate. This means we have converted this hydroxy group into the OTS good living group. So that's what conversion did in this tosylation reaction. And once this converted into good living group, now we can react this P negative, uh, this entire group, entire, we can do the substitution reaction, substitute this O tosylate entirely with this POTS. Sorry, P double bond O PU twice. So that's what we did. This tosylate group is now good living group, and in terms of when we add this nucleophile, cause the P bond directly attack on this carbon, and this OTS group is get eliminated, and we get our target molecule, which was so this one, right? If you look at this target molecule, so there was a phosphorus carbon bond, and that new bond formed in this last chain. So this was the one molecule which has the name Bill fossil. So that the some uh, that's how this retrosynthesis of this molecule has been done. Okay, we'll take the third question. So third example, and here, so this is the Henpirene precursor. So basically, this is a precursor for some of the uh, this target molecule. Sorry, this intermediate is our target molecule, and how we can achieve the synthesis of this target molecule. So here, if you look at here, where we have did this connection, the first disconnection goes here. We get the 2-phenyl magnesium bromide. So this pH negative and this carbon can become from the uh, carbonyl group. So that is here. Since we have to substitute two sites, so that definitely not aldehyde and not ketone. It is as ester because ketone or aldehyde can only gives the one addition or one nucleophile addition from the carbon center. But here from the ester we can add the two number of nucleophiles. That is in this case this is the Grignard addition reaction. If you look closely, the ester convert into the this alcohol by using this phenyl magnesium bromide, and then the previous sorry in the next step or next disc retro from this one was, so this part can be synthesized from this alpha beta unsaturated ester along with this amine. Okay, so if you look at the linear synthesis for this molecule, so this is alpha beta unsaturated ester. So basically, this is the starting, and when we react this starting with this nucleophile, what happens? This negative charge attack here, goes here, this goes here. We get the resonance stabilized structure, and in the second step, what happens in the mechanism? this O negative, get this N. So O negative, right? And double bond goes here. In the next step, obviously it will abstract the proton from the solvent. It gives the this product, right? So this product we get, and once you get this product, so if you add the two equivalent of phenyl magnesium bromide on this ester part, it will gives the our targeted precursor molecule. So this is how the synthesis and retrosynthesis for this molecule is done. So in the chemistry, in particularly in retrosynthesis, more and more examples, if we see, we can basically get the more idea regarding the different retrosynthetic approaches. So here also, this is a similar example where is similar example as seen earlier as well. So we have this target molecule. So how this target molecule can be synthesized? So basically on this position, sorry, the first step was the functional group interconversion. That is basically this ketone can achieve from this alcohol, and how this alcohol molecule is achieved. So by doing the disconnection at this point. So basically the this part is comes from the benzaldehyde, and this other part come from the negatively charged MgCl, that is magnesium Mg phenyl magnesium bromide, but just it is a chloro substituted phenyl magnesium bromide. Sorry, I was got muted. So if you look at the synthesis for also linear synthesis, so this is dichlorobenzene, but alpha ortho dichlorobenzene, and if you add the methyl magnesium bromide, one equivalent, magnesium and diethyl. So what we get? We get this one of these chloro get MgBr. That is the we have prepared now. This is Grignard reaction in the first step, and in the second step we did the Grignard addition reaction. So that's how we can do the Grignard addition reaction. Those in this case, if you look at here, so this will be the negative charge, and this Mg is positive charge. This negative charge attack on this carbonyl center, which is delta positive, right? So, uh, so this negative charge attack on the electro positive carbonyl center, and this O get O negative, and upon abstraction of proton from the solvent, it will be OH hydroxy. So this is part comes from the this chloro part with this to here it is chloro part, and after that this is the aldehyde part, this OH now. And if you do the oxidation just by adding the PCC, pyridium chlorochromate, or PDC, so what we get? We get this our target molecule. So this is basically simple reactions. And so if you look at the reagent different, what are the different reagent possible for this oxidation? So we can use the PCC, we can use the PDC, also we can do the Swern oxidation. Also we can do the MnO2 oxidation. There are n number of oxidizing conditions are possible for this oxidation. Okay, I hope clear for this example now. Now we'll take some toolkits for our retrosynthesis. So this is the secondary alcohol. So basically, how the secondary alcohol generally prepared. So we have the aldehyde and Grignard reagent. We can get the secondary alcohol. But if you want the tertiary alcohol, you can do the Grignard addition reaction on this type of diketone, sorry, ketone. On reactions here, if you want to have the secondary alcohol, we have to or must have to do the reaction on the aldehyde because there is one hydrogen. So that definitely need to come from the this aldehyde part. But if you want to have the tertiary alcohol, we can do reaction on either and tertiary as well. Tertiary in this particularly asymmetric means this R1, R2, R3 they are not equal. Then we need to do the reaction on such keto substituent part. But in our case, as we seen one of the example here, so which one? This one. So this example, what we have basically, we have this alcohol with the R1, R1 and the R2. The two similar are and one is different, right? So in that case, how one can do? We can also do, and basically I will draw this different color, this R. So if you have such alcohol, then this can be come from either R double bond O E T. So basically, and plus R dash Mg Br. So if you look at the color coding, it might be clear now. So this R dash two times can add here one first time and the second time. So it gives the one R dash and the two R dash. So we get the tertiary alcohol in which you can see here the two R are equivalent, but one is different, and that different can come from the ester. So that's what if you have such target molecule, so we can think of this type of approach. That is, it can be we can use the ester as our starting material. Another example, what we can do. So let's say if we have a target molecule and which is a ester, so then how one can how one can approach this type of retrosynthesis. So what we can do, we can add on the aldehyde the required R, let's say R dash mg. So this R dash already there. So this can be R double dash, let's say, or the R2 mg br. So this gives the alcohol that is R2OH along with the original R dash, the which was from the aldehyde. So this is what we get. So better I will reverse this structure. This is the green part come from the Grignard reagent R2, right? And if you want to the ketone for this one, we just do the oxidation. So we can get these R2 like this. So I hope you understand how we can use the different type of approach to get this type of target molecules. So here I will just summarize again. Better to use some different color, maybe this one. Yeah. So if you want to have this type of alcohol, so we can directly simply do or if you want the secondary alcohol, we can directly use the aldehyde and the Grignard reagent, depend upon our the R1 and R2, that sort of the Grignard we can use. If you want the tertiary alcohol with all the three R are different, then we need to have this type of aldehyde and this R1 and R2 different aldehyde, sorry, the ketone, how we can prepare. So that can be prepared by this method. So this method, right? So in which you can see here the R1 and R2 are different, and for that we need to use this type of aldehyde and R2 MgBr aldehyde and the two different sort of one aldehyde, one is Grignard. So we can get the alcohol and we can do further oxidation, get the ketone. So this one is clear. Now, if you want such type of tertiary alcohol in which R2 and R3 are equal. So that is R2. There are two similar and one R is different. So we can simply select this that the different that R1 as a ester and these two different R to MGBR as a Grignard part. And then we can get basically these two equivalent of uh, two R's in our target molecule. And the same example that I have also shown how we have used this. In this case, the two similar Grignard which gives this type of alcohol in which you can see here the R2 and R3 are equal and R1 is different. So this is basically this R1 part is different and the two R groups. So these are just like some sort of small toolkits and the tips that you can use while doing the retrosynthesis. Also, so synthon and their synthetic equivalent I have listed here. So if you look at this is the synthon. So when uh, you are doing this, let's say, if I just show you, this is the R2, this is R1. So better to show with the some color coding for easy understanding. Okay, so in this case, if you want to do the retrosynthesis, and I did retrosynthesis here, so basically this R1 double bond O, this is the positive. This should be the alcohol, right? And here also, I just draw the, this is let's say the syn positive plus this red one will be the R2 negative, and these are the synthons, right? So these are the synthon, and for this synthetic equivalent will be R dash double one O O H. So this will be the synthetic equivalent for this type of synthon, or we can also write so this as a positive like this. So this delta positive here because this is alcohol, so it should be the OH, right? So that's what we are writing here. So there are different type of synthon and synthetic equivalents. So if you look at here, so this is the synthon for this synthetic equivalent will be the aldehyde. If we have such uh, alpha carbon of this ketone are we know they are it is delta negative, right? Upon abstraction of proton it can form here negatively charged. So this is the synthon and synthetic equivalent for this one is this, and we can also write down this R double on O CH3 as well. So this is also one synthetic equivalent for this, right? This is just a base in place of base. In place of base. So this methyl, this one proton from this alpha position to the ketone can be abstracted, and we can get this enolate, and which is synthetic equivalent to this the synthon. Similarly, this is the synthon for the this type of epoxide. So if you look closely here, so on the same carbon on which the hydroxy group is attached, if you want this cation here, so that will be the synthetic equivalent will be aldehyde. But in this case, the synthetic equivalent is this type of enolate. But here the difference is the negative charge on the alpha position. In the second example, sorry, here in this one, now if you want instead of this negative charge, if you want the positive charge, then we can use such type of epoxide. And similarly, if you want the positive charge on the beta position, then we can use this type of our synthetic equivalent for uh, this type of intermediate or this type of synthon. So this will be very useful when we are doing some synthesis. So on this position, basically for this one, let's say, so this is the delta positive. Here we can add any kind of nucleophile. In this case, we can easily add any type of nucleophile at this position. In this case, at this position. In this case, we can add any. Here it was nucleophile. We can add nucleophile, but in this case, if you want to, we can add the electrophile here in at this position, and we can add any nucleophile on this carbonyl position. So this is just like some sort of toolkits for solving some electrostatic problems, and we will see some more example with this. Okay, so this is the first example, and if you remember earlier that I have shown, this is the example of this first synthon and synthetic equivalent. So I will just give the labeling first, or just label as a 1, 2, 3, 4. Sorry, A, B, C, D, and you should able to distinguish which uh, synthon and synthetic equivalent pair you can use in this example. So this is the first example, and if you look closely, so this is basically here what we have now: two synthons OH, and here it is positive. The second part will be this entire phenyl ring. I will just draw in the short form. So by me, okay, I will just draw OH. So this is delta negative. The charges I will draw with some different color. So this is the negative charge and this is the positive charge. So these are the synthons, right? And what will be the synthetic equivalent for these synthons? So this is basically CH3 normal, right? This pH I will just draw this one. And for this one, this hydroxy group, this can become from this sort of aldehyde. Right. So this is what the simple retrosynthesis for this gingerol molecule. And you can now get to know why this such type of such understanding of such or awareness of such toolkits is important. So here very easily we have did retrosynthesis of this molecule. So we have aldehyde. So this is the sorry, this is the aldehyde and this is the ketone. So when we add the base, it abstracts the proton, form the negative charge here, and once this negative charge form, it can attack on this aldehyde, and we get our target molecule. So on this, once the negative power charge form, it can attack on this carbonyl center positive charge, and we get our target molecule here. So that's what our target molecule. So how easily we did the retrosynthesis for this molecule. Further, this is the second example. Now, if you look here, the retrosynthesis will be here on in on this molecule. So I'll just zoom on this molecule. So in this case, if you look closely, so we can do the disconnection here, and what we get, this is enolate, and this is the positive charge, and this can be the synthetic equivalent for this one will be the ketone. For this one is also ketone, same ketone. So in place of base, one of the molecule can form the enolate, and which further attack on the second molecule. Okay, this is the another example. If you look closely, the retrosynthesis approach for this molecule. So this is the double bond, and if you do the functional group inter conversion for this molecule, so basically this will be the hydroxide, and here there will be a hydrogen, right? So this is basically we have here to here. It was just the dehydrolysis reaction. Then now come to our uh, disconnections. So if you look closely here in this molecule, here it can be the disconnection, and this alpha position of this ketone are acidic, sorry, ketones, not this. Will just keep this consistency. So, so here we have the disconnection. So this alpha hydrogens upon abstraction forms the enolate negative charge and which further attack on this carbonyl center. That's what we have this. Uh, that's how we get this molecule intermediate. And upon dehydrolysis of this compound under heating, so we can get this type of olefin alpha beta unsaturated ketone compound. So here also the similar approach you can note down from this one. So I don't think I really need to explain this similarly again. And this is the carotene molecule or the, sorry, carotene intermediate. If you look at the retrosynthesis for this molecule, how it will be basically this first disconnection. It gives this shorter version. So as we seen earlier example, how this how from the two different aldehyde molecule we can basically get the such type of alpha beta unsaturated aldehyde molecule, right? From the two aldehyde. Here also the similar. So upon disconnection here, so basically this is again a aldehyde molecule. Further upon disconnection here, we can get again further here we can get now the ketone because upon doing disconnection here there is methyl substituent here which was absent in this case. It was hydrogen, the ketone, and further if you look at here, this is what the starting material. So the steps involved for this to this retrosynthesis was the similar to this one, the functional group in interconversion and followed by 1,3 di this disconnection. So you just repeated number of steps. In the first step, it was here the aldehyde, but in the second case, we get the ketone. Why we get the ketone? Because there is a CH3 group here, so that's why you get here the methyl group. In earlier case, there was a hydroxy group. So this is how you can just do retrosynthesis of similar such molecules. Now, if you look at the another example, which is very again very similar. So in this case, so upon disconnection here, so we get this aldehyde plus this ester. And how this ester can be prepared? Again, the similar manner. Yeah, this is one I will show the synthesis for this one. So this ester can come from this type of diester, and upon disconnection here, we can get this allyl bromide. So here we will see from the retrosynthesis first, sorry, the linear synthesis first. So this is the diester, which has this diester or diethyl malonate. And if you look at here, it has the two hydrogen group upon addition of the base and the allyl bromide. So the first allyl bromide adds here, right? Because base abstract the proton from this position, and upon abstraction of proton, it forms the enolate followed by the substitution reaction of this allyl part, right? Once this allyl part is formed, now the second step was further in place of the base NO80. Now what we have? We have here one hydrogen. So in place of base, this forms the enolate again, the second enolate. So basically, it forms this negative charge here, around OET. This negative charge further attack on the this aldehyde, and what we get? We get the C double on O ET, another C double on OET, and from this aldehyde we get this hydroxy group followed by this phenyl ring will be as it is with this OEME part. And now if you look closely at this molecule, so this is very unstable, mainly because there are two carbonyl groups on the same carbon. So what happens in terms of the NaOH and the base? So decarbonylation reaction, as mentioned earlier, occurs, and we get the elimination of this entirely one group in place of NaOH and heat. So we get our this target molecule in these three steps. So this is just the, if you draw this hydroxy group on this side for better view. So that's what our target molecule. Right. The next step here is the, sorry, next example here is for the seventh or eighth example, maybe eighth. So synfumide. So this is the structure of synfumide, and if you look closely, how the synthesis of this reaction, how the retrosynthesis of this one works. So this will basically first disconnection here, which maybe come from the acyl chloride, and the another part is the amine, right? So this is the this acyl chloride can be further comes from these uh, acid. Just by this is the just functional group interconversion state, and this acid entire part plus this other part. So here there is double bond, and as I shown earlier, so this can be here the disconnection. So this can be from the aldehyde, and now this from the this type of acid. So if you look at the how this retrosynthesis, sorry, the linear synthesis also for this molecule. So the first step was just addition of the sorry, not directly base, because this if you add the base, this hydroxy, this proton from this acid can be so base plus acid, it can form the salt. So we can directly add this base to based on this one. So if you look at the linear synthesis, so this acid part, as we seen the use of this diethyl malonate earlier also, this is will be like this. So we can use the, instead of directly using acid, we can use this diethyl malonate because in place of directly this acetic acid plus, let's say, as we see earlier here, so that was the starting CH3 double bond O OH, and if you add the base to abstract this proton here, proton on, sorry, to abstract this CH2, this proton, because we need to abstract the proton first and then need to attack on the aldehyde, right? So that's what our approach. So negative charge, we can prepare negative charge here by abstracting the proton. So once this negative charge form, this can attack on this aldehyde, and we get such aldehyde followed by dehydrolysis, we can get such molecule. But that approach we can't use. We have to use this diethyl malonate, because if you add the base, this acid plus base, they can form the salt, and the reaction just get stopped there. But if you have this diethyl malonate, so in the diethyl malonate, uh, not also this malonic acid, these protons are more acidic, uh, and they are very labile protons. So just by adding a little mild base condition, so this can easily abstract, these protons are easily get eliminated from the anion at this position, alpha position, and this can further attack on this aldehyde. So we get the intermediate, in which if you look at the intermediate, what intermediate we can get with this one, we get this OH followed by this intermediate. And if you look closely here also again, so this is the very, this acid group, two acid groups attach on the same carbon atom, so it's unstable intermediate, so it goes undergo decarbonylation to get use this intermediate. So this hydroxy group as well as these groups get eliminated. So how this eliminated, if you look at the reaction mechanism for this elimination reaction, this O and this H. So I will just show the arrow pushing. So this goes here. Once this goes here, so this can goes up and can further potentially comes down, and this bond goes here. Once this bond goes here, it form anion at this center, or directly it can move to, so this bond goes here, hydroxyl group gets eliminated with this O negative, OH negative, and we get this double bond in the product as shown here. So that's what we get in this reaction. And once you get this product, so what we can do, this acid can convert into the acyl chloride by using this SOCl2. And so this is just a C double bond O, Cl, and this is R group, like this entirely, remaining part. right? So this R group. So SOCl2 react with the acid gives the acyl chloride, and when we add the in the similar same reaction mixture, we add the this amine, so it gives the basically amide, right? So this amine can attack on this acyl chloride, so this chlorine get eliminated, and we get the our target molecule. So this is what the synthesis for this syn synfumide molecule. Any doubt in this one?
No, it's okay.
We'll move to the next some problems. Okay, so this is another problems, and again use of similar diethyl malonate can found here. So this is our target molecule, and if you want to do the synthesis of for such molecule, so this part can be come from this diol acetal. So basically, this is just a 1,3 hydroxy protection have been done here. Then, if you want to convert this into more simple molecule, so this hydroxy can become from this diesters. And if you want to further break down this molecule to the much more simpler one, what it can be like this. And here there should be some living group, right? And the other part is like this. So basically what I have did. So here also further we can do the further disconnection. So to get the more simpler molecule. And if you want to further do living group, or we can also write down here the proton. If you want to do the further references for this molecule as well, this molecule, then it can be potentially this N and dimethyl can be come from the, sorry, I will just write down in the some. Okay, if you want to break down this molecule further, so this can be here not the living group, but here it should be the hydrogen. We can break down this molecule to this, I mean, ketone plus this dimethyl amine, like this, and hydrogen, like this normal diethylamine. So NN dimethylamine, methyl, and the hydrogen. So like this, because aldehyde plus imine, when they form react, it form the imines. So that's what, and further imine reduction, we can get this further amine as well. by this imine reduction uh, can be done by NaBH3CN, sodium cyanoborohydride. So that type of reaction, I think we have shown how we can do the imine reduction. So that's what we can use here. Okay, so if you look at the come to our question, if you want to do the linear synthesis for this molecule, so we can do in this manner. So this is the aldehyde. So aldehyde, when react with the diethyl malonate, it can form this alpha beta unsaturated diesters, right? And when it react with this NN dimethyl amine, so this diester, this amine can attack on this position of this diester. It forms a negative charge here. We can get this intermediate, and upon reduction with this LiAlH4, this two ester groups get converted into the diol groups. So the intermediates will be like this. Diol, and further on reaction with this of this diol with this aldehyde plus BF3 thread, BF3. So it gives this diol protection. That's the acetyl group we can get. So here, as you seen here earlier, what I have mentioned here, that further the breakdown, the similar, the more simpler approach is as shown here in the. Oh, sorry. I was just like I was unmuted. Okay, I will explain this again. As somehow I have my mic was muted. Okay, so I will explain this again. So how the synthesis for this molecule works. Okay. So as I have shown the disconnection earlier, uh, as I have shown the earlier disconnection, we can do the disconnection here. But instead of doing disconnection in this position, if you perform the disconnection here, that will be easy. Why? Because upon doing disconnection here, so we can easily get the this type of this type of two synthetic equivalent, right? Uh, sorry, these two type of starting materials, and this starting material further we can break down this starting material to uh, like this. So basically, this is the aldehyde part, and the another part is now we can do the disconnection here from this one, and the another part is diethyl malonate, like this. So these two starting material we can get here. Okay, and if you look at the linear synthesis for this same linear synthesis, so this is the aldehyde plus this diethyl malonate. Upon the reaction, what they form such intermediate step, so which involved uh, which forms this. When this negative charge form impress of base, it attacks on the aldehyde. So this aldehyde, it attacks on this aldehyde. So it gives the alcohol here, right? And alcohol with this C double bond O E T, and here, sorry, here again there will be again further C double bond O E T. And now if you look at here, there are two uh, one hydrogen hydroxide and this group. So in presence of base, what happens? So this proton is still again acidic. So in presence of base, this acidic proton get further affected and it forms negative charge which further eliminate this O negative. So basically dehydrolysis step occurs here because of the base, and we get the intermediate which is this one. Sorry, yeah, so we get the product. So this was the intermediate. We get the product, this one, and which is the diester. So upon addition of this dimethyl amine, this dimethyl amine attacks on the 4 position of this not 4 position, the beta position of these carbonyl groups, right? Because this is the electropositive center which I have seen, we have shown here in the our toolkit also. So where, yeah, here. So if you have such position to the this one, so the beta position, that is this position, is electropositive. And here, similarly, this amine attack on this beta position, we get this diester with this amine substituent now. And when we perform the reduction reaction with this lithium aluminum borohydride, sorry, LiAlH4, so these esters get converted into the diol, and this diols will be looks like this. And upon reaction of this diol with this formaldehyde, the reaction of this diol with the formaldehyde plus BF3 thread in catalytic amount, BF3. So it gives this acetal formation, and which is our product. So in this example, we have seen multiple reactions like reduction of the this esters followed by this acetal formation. This was the last step. However, in between we have seen this reaction, this addition of this amine on this 4 beta position. This is called a this is like a So this electrophilic position, the beta position. So on the beta position, this nucleophile shows the addition. And the initial earlier, the first step was the this usage of this malonate ester on the to form this enolate, followed by addition of this negatively charged enolate on this aldehyde. That was the first step. So multiple steps are involved in this retrosynthesis for this molecule. Further, this is the one example. I have used this one mainly to show. Uh, so if you look at this example, this is mainly basically just a linear synthesis that I have shown, but the reagents usage here is important. So if you look closely, whatever example that I have shown today, it was all belongs to the alpha position of this keto group. But similarly, alpha position we can easily abstract and we can form this negative charge on this keto. But similarly, there are certain other molecules also, like the nitro is one of them. On the alpha position of this nitro group also, we can basically CH2 3. On this alpha position also, we can form this negative charge. Very similar reaction works as like the our as shown earlier the ketone or the carbonyl compounds. So on this example that I have shown, we have this CH3 CH2 NO2, right? And in presence of base, what happens? The negatively charged form on this alpha position to this nitro. And once this negative charge form, and if you have look at the starting, what we have, so we have here the beta position of this carbonyl vacated, the empty, so we can get this very easily attack of this negative charge here, and basically we can get this carbon attached to this here this nucleophile attack takes place, right? We get this product. So this is entire addition of this nucleophile, and since this uh, negative charge form on this position, so that's the position, that's the carbon atom here. So this is what we can get in the first step. And what is the reagent condition? Just a sodium methoxide and THF, right? So this is what we can get here. And further here, this is the one of the NAPE reaction. If you remember, this is the NAPE reaction. So this nitro group, we can convert this nitro group to the ketone group in this NAPE reaction. And what we can do, what are the reagent? Sodium metal, methanol. Further, second step was the H2SO4 and the methanol at minus 0 degree, minus 50 degrees Celsius. So this is the NAPE reaction, this nitro group. Now we can convert this nitro group to the keto group using this reagent condition. And this is what I want to show for this one. And this is also the conversion of this nitro to the keto by using this sodium metal, methanol, and the uh, influence of acid at minus 70 degrees, minus 50 degrees Celsius. Okay, so I hope it's clear up to now. So we'll stop here for today, and I will cover some more name reactions maybe in the next video, because tomorrow early already the professor is gonna take the interactive session with you guys. So make sure you guys attend this interactive session with the professor, and also ask any doubt, and also discuss with the professor about the course, give the feedback regarding what you are learning in this course, and how we can also, if you want to have some further interaction with the professor, you can have with this in this live class. So that's what all for today. So if you guys have any doubt, please let me know, or we'll stop here for today. Okay, we'll stop here for today, and we'll see in the on next Tuesday.